This device is accurately able to count to 1 minute before resetting back to 0 seconds. How does it work? It is broken down into 6 main stages. The first stage was establishing a 1 Hz time base. This stage uses a quartz crystal which has a special property. They are able to vibrate at a stable frequency when a voltage is applied. In this case, the crystal vibrates at 32,768 Hz. Now, the circuit needs to have a frequency of exactly 1 Hz in order to accurately count to 1 minute. To get it down to 1 Hz, 2 chips can be brought in to do so. 32,768 is also known as 2 to the power 15th. A CD4060 integrated circuit is able to divide by up to 2 to the power 14th, which means that it can get it down to 2 Hz, which is 1 Hz too many. Then the CD4D13 can be used with the flip-flop mechanism to configure into toggle mode to divide the signal one more time, producing a final 1 Hz output. This meant the circuit generated 1 pulse every second. The second stage focused on binary coded decimal, or BCD, counting using the CD4518 and the CD4081 AND gate. In BCD, each decimal digit is represented using a 4-bit binary sequence. Every 1 Hz pulse from the crystal increased the count by 1. When the circuit reached 60 seconds, the AND gate detected the binary pin for 6 and automatically reset the counters back to 0. The next step involved 2 CD4511 decoder chips converted the BCD outputs into signals for a dual 7-segment display. These displays are seen in everyday life, whether it's calculators, crosswalks, or alarm clocks. As the name suggests, each digit has 7 segments on the display, assigned a different letter from A to G. In the circuit, 2 4511 chips are used to decode from BCD to 7-segment. 1 chip is for the units and 1 chip is for the tens. Before the display was added, LEDs were added onto the outputs to ensure that it was working properly. Then the display was added and the outputs from each of the chip were connected with a corresponding letter on the display. This allowed the numbers to be displayed visually. Lastly, 4 resistor networks were also added to limit current and protect the LEDs from damaging. Once the breadboard prototype was finished, all the pieces could be transferred to a printed circuit board and soldered on. Then, they were screwed onto a 3D printed case and the device was finalized. The final device was be able to turn on and off and also had a reset button that the user could reset the device manually.